Hi guys, this is a video about the binomial theorem, which is a topic that students in IB1 traditionally find difficult, and their difficulties are mainly in kind of understanding the notation and in algebra. So I'm just going to recap the binomial theorem for you and do two kind of classic question types about the binomial theorem. And you can watch this video as you study and pause and work along with it, stuff like that. So what is the binomial theorem? The binomial theorem is essentially a theorem that lets you quickly expand expressions like this, which is a binomial, x plus y, raised to some power, n. And of course, you could use the distributive property a bunch of times, right? N times, if you wanted to, and you'd essentially spend a very long time foiling or distributing everything out. So we actually look for patterns to create a shortcut to do this. And you see, okay, let's look at x plus y to the power 1. Okay, well that's just x plus y. X plus y squared, that's x squared plus 2xy plus y squared. And let's do one more. So that's, let's see, really, do we take x plus y squared? So what we just calculated. And we have to multiply this by x plus y one more time. So let's see, we get x cubed plus x squared y plus 2x squared y plus 2xy squared plus xy squared plus y cubed. And let's clean this up. X cubed plus 3x squared y plus 3x y squared plus y cubed. So maybe already, if we look, we see some patterns starting to emerge. For instance, in each of these, we notice kind of the powers start at the power of our expansion on the x term and count down. So we have 2, we have 1. This is really x to the power 0. Whereas on our y's, the y's start at the power 0 and count up all the way to the power of our expansion. Okay, so let's look at the coefficients now. Like, for instance, if we look at the expansion of x plus y cubed, we have a 1 as our first coefficient, then we have a 3, then we have a 3, then we have a 1. And so if we know the patterns in the x's and the y's, really we just have to look at the pattern in the coefficients, and then we'll know all the patterns in this expansion. A quick way to look at these is to use something called Pascal's triangle, which is a very famous triangle with a lot of history behind it and many interesting patterns contained inside of it. So basically, in row, we call this row 0, we start counting at 0, we have a 1. Oh, let me turn. So we have a 1. In row 2, we have 1, 1. And the pattern in the rows of this triangle are each row has one more term than the row before it, and the outside rows are always 1. So you have 1. Now if you're on an inside position, you add the elements above it. So 1 plus 1 is 2. Outside is 1. 1 plus 2 is 3. 2 plus 1 is 3. And let's do one more for good measure. 1, 4, 6, 4, 1. Now, let's look at x plus y to the power 1. We have coefficients 1 and 1. Oh, that looks like row 1. Remember, the first row is row 0. Let's look at x plus y squared. Now we have 1, 2, 1. 1, 2, 1. That's row 2. And if we compare to row 3, 1, 3, 3, 1, that's the same as row 3 in our triangle. Row 3. So the coefficients in a binomial expansion are the elements in that row of Pascal's triangle, the row corresponding to the power grid expansion, which is completely amazing, but it works. And we can talk about more why it works in class. So we have a labeling scheme. Some people decided, oh, well, let's label the elements by their row number and their column number starting at 0. So row 0, entry 0 goes like this. Row 1, entry 0, row 1, entry 1, and we can label our entire triangle. This is just a labeling scheme for the elements, so on and so forth. So if I tell you, oh, what is 3, choose 2, you go to row 3, 0, 1, 2, 3, over 0, 1, 2. So this is 3, 2. And these symbols, which we read as, say, depending on which one, like this one I'm circling, this symbol is called 3, choose 2. In class, we went over a combinatoric interpretation of this symbol, meaning it's a number of ways to choose 2 elements out of 3. But we're not going to focus on that in the video. Okay, so having said all this, we've established the pattern. The binomial theorem states that, write this one in black, if you have a binomial and you raise it to the power n, it looks like this. It's n, choose 0, so go to row n, take the first entry. X starts up at the highest power, y starts at the lowest power, and then we increase this number, this what is 0 here, by 1 every time. So, so let's say next we get n choose 1, the x's count down, the y's count up. And choose 2, next. And this keeps going until the last element in that row of Pascal's triangle, x is then at power 0, and y reaches power n. This is the binomial theorem. And if you prefer sigma notation, which we learned in class, that can be expressed like this. I wouldn't get too hung up on this notation, but it is a more compact form of expressing the binomial theorem. The last thing I will remind you of that we learned in class is that if you are calculating some very large value of n choose k, or some value where you're only computing one of them, you don't want to write out the whole triangle, we have a formula for m choose k. This is in your formula booklet, and it goes like this: n factorial over k factorial times n minus k factorial. So that formula can be useful, especially if you just want to calculate one value of n choose k. Okay, so let's look at some common types of questions you may be asked to solve involving the binomial theorem. So here's one example. Just do an expansion, 2x plus 3y cubed. Okay, so this is very similar to the kind of x plus y cubed we looked at before, except now our x's and our y's have coefficients in front of them. So let's recall that if you, let's instead of x and y say, okay, so this is the binomial theorem. It's, we add up all the terms that look like this. Until, and remember these n choose 0, n choose 1, those coefficients are the entries in the nth row starting at 0 of Pascal's triangle. So we see we're going to have to go up to the third power, so we need to draw the first 3 rows starting at 0 of Pascal's triangle, which look like this. And instead of an a here, for us, a would be 2x and b would be 3y. So let's use the binomial theorem. It says, okay, it's 3 choose 0 times 2x to the 3. So notice that 2 is in the brackets. It's getting cubed. The whole first term in our binomial gets cubed times 3y to the 0 plus 3 choose 1 times, now the powers on our first term count down. The powers on our second term count up. And we're always going to have, notice, one more term than the power of our expansion. And 2x to the 0, 3y cubed. Okay, now let's simplify. 3 choose 0, that's this term is 3 choose 0, this one's 3 choose 1, this one is 3 choose 2, and this one is 3 choose 3. So 3 choose 0 is 1. Now this is 2 cubed x cubed times 3y to the 0 is just 1. Plus, okay, 3 choose 1 we see is 3 times 2 squared x squared times 3 times y if we expand all the brackets. Plus, okay, 3 choose 2 is also 3 times 2. I should be consistent with how I write my times here. 3 times 2 times x times 3 squared times y squared. Plus 3 choose 3 is 1. Anything to the power of 0 is 1 times 3 cubed times y cubed. Okay, and let's simplify this further. So this is 8x cubed plus 3 times 4 is 12 times 3 is 36. Here we've got 3 times 2 is 6. 6 times 9 is 54. And lastly, 3 cubed is 27. So there we have it. Our expansion, 2x plus 3y all cubed, gives us 8x cubed plus 36x squared y plus 54xy squared plus 27y cubed. So this process, although it wasn't quick, it will become quicker for you, and you don't have to show every single step that I did, and it's definitely a lot faster than writing out 2x plus 3y times 2x plus 3y times 2x plus 3y once you get the hang of it. Now the other type of question you'll often see is one where you have to calculate a specific term of a binomial expansion. Now it'll be a lot of work even with the binomial theorem to expand a binomial to the power 6 or 10 or bigger. But it's not too much work to calculate one specific term. And why is that? Well, remember, if we have, let's say, some expansion, a plus b to the power n, well, each term looks like, well, let's see what we have, n choose 0, a to the n, b to the 0, plus n choose 1, a to the n minus 1, b to the 1. And remember, each kind of generic term in the middle is n choose k, a to the n minus k, b to the k, and then, we keep that going. So each term in the middle kind of looks like this. Kind of looks like n choose k, a to the n minus k, b to the k. That's sort of a general term in a binomial expansion. So we can even write that down as a rule, kind of a general term in a, oh no, I keep doing that, sorry. A general term in the binomial expansion a plus b to the n looks like what? It looks like n choose k, a to the n minus k, b to the k for some k between, myself some more room, between 0 and k. So we have a formula for what each term in the expansion of x squared minus 3 over x squared to the 6th looks like. We just have to figure out which k value we need to plug into the formula. Okay, so let's keep this kind of information to the side so we can reference it. And I'll solve this problem in green ink here. So x squared minus 3 over x squared to the 6. I mean, that looks like it's we add up for all the k's between 0 and 6, terms that look like this. 6, choose k, times x squared to the 6 minus k, times negative 3 over x squared to the k. Okay, so let's see. So in other words, the general term has the form 6 choose k, x squared to the 6 minus k, negative 3 over x squared to the k. So we want to know the constant term. That's the term where the x's have power 0. X's are only a variable. Constant means there's no variable appearing. So x needs to have the power 0. So we need to figure out which value of k we can plug into this to have x be to the power 0. Now it's a little tricky because on the one hand, we have an x squared, which is getting raised to 6 minus k. On the other hand, we have a x squared in the denominator over here, getting raised to the power k. So the next step is to kind of simplify your general term. So this is, let's see, 6 choose k. Let's leave that alone. This is x to the 12 minus 2k. Let's see, okay, so this is negative 3. Let's just write this as, change our x squared to x to the negative 2. And we see we can simplify that last bit. Again, that's, let's see, that's negative 3 to the k times x to the negative 2k. Now we have an x to the 12 minus 2k and an x to the negative 2k. We can combine those. We're multiplying with the same base. So we add the exponents. This is x to the 12 minus 4k. Remember, we want to have 0 as the power that we're raising x to. So really, we want 12 minus 4k to be 0, meaning we want 12 to be equal to 4k, so we see that k should be 3. So if we plug in k for 3 for k, that will give us a constant term. So we must substitute k equals 3 into the general term. Okay, so let's do that. So the answer we're seeking is 6 choose 3, negative 3 to the 3, x to the 0. All right, so the coefficient is going to be whatever 6 choose 3 times negative 3 cubed is. All right, well, remember we have a formula. 6 choose 3 is 6 factorial over 3 factorial times 6 minus 3, which is also 3 factorial. And we have some tricks for this we went over in class. 6 factorial is this. And we can do some canceling now. Okay, let's show some steps. 6 times 5 times 4 over 3 factorial is 3 times 2 times 1. Now let's see. Well, 6 and 3 times 2 are the same thing. So this works out to be 20. Okay, so it is 20 times negative 27, which is equal to negative 540. So that means, what does this mean? If we expanded x squared minus 3 over x squared to the 6, one of the terms, the term that doesn't have any x powers on it, would be negative 540. So this is a very common type of question you'll see regarding the binomial theorem. And they won't always ask you for the constant term. Sometimes they'll ask you for what is the x squared term, or what will be the x cubed y term, something like that. So you can have a variety of types of questions, but they all boil this down to the same thing. You want to look at what does the general term look like, and what k value will give me the term I'm looking for. Then you just plug it in. We'll do tons of examples in this in class, but I just wanted to put one on the web for you guys to see.